In this problem, we're given 4 different parts, and we're going to solve for each of them. The information that we're given is that the voltage across terminals of a capacitor is 0.40 microfarads. So if we were to draw a capacitor, we'll draw something like this. And the voltage across from them is 0.40 microfarads. And we can basically say that the capacitance is 0.4 microfarads because remember, capacitance is measured in farads. We're given some different voltages here with some missing components. Looks like we're going to have to find those later in our problem. But for part A, we're going to be dealing with work or energy. There are notes linked in the description with a bunch of formulas that'll help with the entirety of circuit analysis. But we have this formula for work for capacitance, and we can plug a few things in. Now we know what our capacitance is. This is the 0.4 microfarads. We know our voltage if it's less than or equal to 0 to be 25 volts. And if we look at part A, we can see that T is equal to 0. This is exactly what we want. So we're just going to multiply this by 25 volts. And it wants our answer to be in microjoules, so we don't need to convert any of the microfarad. And lastly, our voltage, because of the formula, has to be squared. And this is going to give us a work of 125 microjoules. So that is the answer for work. Now we're going to look at part B, where we find coefficients A1 and A2, and this is for our voltage. When looking at them, we can see that they're both equal to 0. And if they're both equal to 0, we can actually set them equal to each other. And if we do that and then factor out the e to the negative 1500t, this is going to be our equation. Now, we said that t is equal to 0, so we have to plug in t is equal to 0. We're going to plug this in here and this in here. If we do this, we are going to cancel out this. This is going to just be completely wiped out. And then we see that we have our a, because this e to the negative 1500 times 0 is just 1, since anything to the 0 power is just 1. Now we have to look at our A1. Well, we obviously cannot solve A1 the same way, and we won't be able to just plug it into our work formula. So the next thing I could try is plugging it into the current formula. And the formula looks like this. We have a current that's equal to capacitance times the derivative of our voltage. We know that initially, the initial current in the capacitor is 90 milliamps. So we're going to plug this in for our I of C. And we know that our capacitance is 0.4 microfarads. And this is constant. So we can just divide this like this if we divide both sides by C, just so we can get the derivation of voltage by itself. And looking at this formula is what we're going to have to divide. From here, I'm going to divide this left side out, and then I'm going to factor out the e to the negative 1500 t's again. And this is going to be our final equation. So now we can just plug in our 0 for the t's. And if we do that, we're going to see that all of this is just going to turn into 1. We know that our a of 2 is 25. And then this is just going to be a of 1 also. So really we have 225,000. And then we are going to add this with the 25 times 1500. And the reason why we are adding this and not subtracting it is because we're moving it over to the other side. If we do that, we're going to get 262,500. And that is our answer for A1. Now we're going to solve for C and D. They're very similar, just with different time values. So we need to find the current, and then we are given the time at which the capacitor current is. So looking at this, I'm going to use the current formula again that we have here. We need to find our I of C, or in this case, it's our I of T. So we're going to set this equal, and then we know our capacitance, it's 0.4 microfarads. This is always constant throughout the capacitor. And we also know the derivation of our voltage if it is greater than or equal to 0. We did that right here. So I'm just going to copy this part, because this is going to be the same exact voltage, and place it next to our I of T. So this is what we're going to use, and now we're just going to plug in our values. Into this T, we are going to plug in a 0.4 times 10 to the negative cubed seconds, also in this T as well. And for this, we are just going to plug in 25. And for our A1, we are going to plug in our newfound A1, which we know to be 262,500. If we do all of this, we are going to get that our I of T is equal to 0.148. However, we converted all of these to the normal units, so this would be in amps. And we want our answer in milliamps. So we're going to have to multiply this by 1 milli over 10 to the negative cubed, and then we're going to move the decimal over 3 places. But I put the decimal in the wrong place, of course, so now I fixed it. It's 0.0148 amps. And now if we move the decimal place 3 to the right, we are going to get 14.8 milliamps. And that is the answer for our first IT. Now we're going to do the same exact thing. I'm going to draw this in blue though, and instead of the 0.4 times 10 to the negative cubed, we're going to have 2 times 10 to the negative cubed inside of here. Everything else is going to stay the same. So this will stay the same, and so will this. So we're just going to go back into our calculator, go up, and change only two things for our t. And after we modify our previous calculation, we're going to get that our new I of t is equal to negative 0.0112. We need to convert this again, so we're going to move it 3 to the right, and then we get negative 11.2 milliamps. And that's how you would go about solving this problem. The wording is a little bit tricky, but after you get around that, it's pretty easy, just plugging it into formulas and checking to make sure if it's right. If you have any questions about the material we covered, you can leave them in the comments below. If you want more intro to circuit analysis or inductance or capacitance, there's a playlist and notes in the description.